Good morning. Welcome to Krishna's class. We begin with another series, which is a continuation of the Lebesgue integration theory that we have explored, and this is the abstract integration theory, or in some sense, a generalization of the integration theory. This is going beyond intervals or Rn such situations, so that whatever we develop would be suitable for application on a wider settings. Now, before that, it is worthwhile to recall what we had been doing all along. And we will try to retrace the whole path of integration theory as I have understood it. With the advent of the concept of limits, the concept of derivative came into being. For functions like the standard functions that we were used to, like the polynomials or trigonometric functions, or we call exponential function, and so on. We had been able to compute what was defined as derivative as a consequence of the introduction of the limit concept. Now, it so happened that it was not accidentally done, but it was found that many physical problems, the concept of derivative is significant, and calculus was essentially developed to work on problems of physics. You see that you have the position vectors, then their derivatives giving what are called the velocity vectors. Then their derivatives, I mean, looking at the velocity field as a function of position of time. Once again, you take the derivative, and then you get what is called the acceleration. I mean, these kind of physical interpretations are there. It is for this purpose it is developed, and essentially by Newton and Leibniz, with the pioneering work in this regard. Now, then the following problem came up. What was it? Given a function f, I am talking about elementary functions. Given a function we have its derivative is d by dx of x, or f derivative of x is again a function and in the case of elementary classical functions, in many cases we could compute it. We could compute them as elementary functions. So there was a connection between a given function and its derivative. When we worked with the standard elementary functions, then the like the polynomials or trigonometric functions or exponential function, and then there are various combinations, because differentiation had some nice properties which could be exploited to compute the derivative of product of functions, and then sum of functions or linear combination of functions, and then all sorts of combinations that you can make. And therefore, one found that you have the following, that is f derivative of x equal to some function of x. Okay. So the question is the inverse question. Given the function, you can compute the derivative. But now suppose a function is given, can you find a function capital F whose derivative is equal to the given function? So the inverse problem. F. How to find a function capital F if it exists? These are all modern questions that you handle. Given a function, does there exist a function capital F, first of all? And if so, how to find it out? And in many examples, we found that elementary functions differentiated will give you elementary functions. Their combinations also give differentiated will combinations, and one could really do handle a large class of functions in this way. But now the problem is, given f, how to find this capital? Now this was resolved in the following way. Okay, you have a function capital F. It can be differentiated. There is a standard procedure, and if the procedure works, you get a function fx. So you say that if small f is given, then capital F is the function from which it comes. That means you have this one, f derivative of x equal to f of x. Now f derivative was, or f is called the antiderivative of small f. And for standard functions, we made a huge list of antiderivatives. For combinations, there were some with the known mathematical techniques. We developed methods of finding the antiderivative of given functions. We could some techniques to find the antiderivative. And of course, the antiderivative fx was integral a arbitrary constant, because it was found that the derivative of arbitrary constants a is a is 0, and therefore addition of any constant to this integral will not make any difference. Okay, so in other words, what you are saying is that the antiderivative is not unique. The antiderivative okay, that's one of the observations that we, and this is the symbol form universally accepted. Even now it is used. Okay, that's about the classical part. Okay. Now, ever since the 16th century, when the concept of limits appeared on the scene, this kind of developments came. Concept of derivative came, concept of higher derivatives came, and so on. And of course, systematically leading up to some different differential equations. As you can see, that this itself is a differential equation. Given f, find k. Okay, so it's an inverse law. Okay, so let us leave it at that. Now, what happened later was exploring, is it possible to go beyond these elementary functions? Because the functions itself grew beyond the elementary functions. Because one could formally define a function as a map from, say for instance, the real valued function of a real variable is from, say, some interval a b. This is a real valued function. Okay. Now, the sort of examples that we have been dealing with are the elementary functions fit into this frame. And then, but there are many more functions of this class. Now the question comes, two questions are there. Can you talk about the derivative? So the concept of derivative, then concept of integral. This problem was tackled by using the geometry. In what way? Okay, so let us now, for the time being, let us not identify this with the antiderivative at all. Okay. For the time being, let us forget about the connection between the integral that we are going to define and the antiderivative. We will come to that. So given f, suppose, see, from that real value function, on the interval, we take compact. Can okay. Now we define in integral forms. Later we will connect it. Okay. We shall introduce the concept of Riemann integral. Associating with the function the area enclosed between the, the x-axis, coordinates at A and x equal to B, and the graph of the. So this was called the integral. Okay, so what is it? Let us draw a figure. Now we take then the graph is something like this. Need not be continuous, but let me draw the picture as continuous. This is the interval AB. Now this area measure, and this is what was called the integral of. So this is y equal to of x. This is the x-axis. This is the y-axis. So this is what's called integral a to b e. Okay, how was it obtained? Now we take it for the function which is non-negative, and you can work with any function. After having obtained this, you can work with f equal to, okay, we define, okay, I will come to that later, but for the time being, let us see how it can be. So this is done in a very natural way through approximations. So what we did was partition the interval AB intervals as follows. And maybe boring, but still probably I go through the whole process. And what you have is this, the following. So we take a partition to be itself set of points contained in AB with A equal to x0 less than x1 less than x2 so that is the partition. general partition. Now for each partition, we define two this is xi minus 1 to xi. Now we will work out this. And this is approximated in two ways. One from above, one from below. So each of these, over these intervals, the corresponding strip is approximated by rectangles from above and from below. Now one observes that under the conditions we have, stated, see this is, you see that summation of 1 to n infimum of x over x belonging to I minus 1 psi multiplied by the length xi minus 1. This was designated as what are called P is a partition. Similarly, times xi minus 1 upper sum. This is are the two definitions that we make of lower sums and upper sums. Now you observe that the lower sum we also observe that if P1 and P2 partitions such that P1 is contained in then F and U P1 of F greater than or equal to this inequality is there for P1 contained in P2. Now let's all the partitions of then to see that suppose you take these numbers yes E belonging to is bounded below by a lower sum. By a lower sum, needless to say that. By any lower sum. So also is bounded by bounded above any upper sum. So you have now two sets of numbers. One is bounded below, the other one is bounded above. Therefore, supremum of over P exists and infimum of UPF exists. Okay. Now you call this the upper integral. So you call this. So this we designate by what is called the lower integral. Okay. This we designate by what is called F. LF and UF is equal to CF. Now this is the question that we are asking. This is not universally true. Okay. Even for bounded functions, on the interval AB, this is not true generally. However, for a huge class of functions which we encounter usually, like for instance the continuous functions. They are in. In fact, for all continuous functions, on AB equals. Okay. And for many more functions that we will ask for which class of functions this is true. That's a finer question that we ask. But before that, in general, you have sufficiently large class of functions for which this is true. For functions f for the time being, this is an artificial restriction. We say that for which say that f is Riemann. F is Riemann. So this is the criteria for Riemann. For non-negative functions, for the time being, now we will take it beyond. Now for functions, not necessarily non-negative, not necessarily non-negative, we can split f as a sum of a difference of two non-negative functions. Minus as follows. What does this look like? Comes as f plus is zero. Then you have fx equal to minus x. Okay. And for this we write, we extend Riemann invariant by defining, it's a well-founded definition, it's not artificial. because the integration is a linear operation. That's the reason. Now you see that in both these cases, f plus and f minus, whatever we have defined works, and therefore this is the definition of integral. And you see that for all yeah. So you see that if for f plus and f minus are integrable, then f is integrable. That's the reminder. Now you see that the question that you ask at this stage is which functions are Riemann integrable. So the answer to this is bounded functions not all bounded functions with or what you call length of discontinuity is zero. And vice versa. In fact, this is a nice result. Which functions are Riemann? Take all bounded functions on the interval AB with the set of discontinuities forming a zero length set. Okay, this is a pointer to the concept of measure, or you can say that more sophisticated terms. So this is the, and you go to the definition. I don't want to, but that is not the point. The point that I want to make is you can characterize such functions. That's fine. But the point that you want to deal with is this. How is this related to antiderivative? This is the question that you ask. How is this related to the antiderivative? Now one proves the following. Suppose fx is defined as this is a Riemann integral. We are working with the Riemann integral functions. The class of all Riemann integrals. Okay. Now the question that you ask is this: is f the antiderivative of small f? This is a question. This is what we are expecting to be true. Now one can show that for all smooth functions, this is true. Means continuous functions with continuous derivatives. This is true. Or smooth functions, this is true. But is it true universally? But is the answer to this is not true. The answer to this is a big no. But locally, one can talk about this differential. So where, or at least where this particular differentiability holds, one can investigate you cannot say that capital F is differential. You can find functions which are Riemann integral, from which you can pick up the particular f, but f derivative may not be. Now this is the problem. So this is not this antiderivative identifying integral. So this is a problem. So our classical notion of integral being the inverse of differentiation fails. Okay, right? So integral being looked at as integral is not equal to this is a major casualty, except in This is what we have seen. So our perception that integral is anti-derivative breaks down. Our initial perception that integral is the anti-derivative is no more. But certainly it is an extension of the anti-derivative concept, or it is can be it's an extension of the anti-derivative. That's interesting part. So what next? We are not worried about that because at least this you get a very worthwhile extension of the concept of derivative, or we are progressing. Okay, we are progressing. It is certainly for all for all nice functions. They are. So we are actually progressing forward, and we have generalized the concept of anti. That's a interesting observation. Successfully, that's an achievement. Okay, that's one thing. Now what next? We go in different direction. See, meanwhile, the mathematical analysis was moving forward, and instead of looking at individual functions, we started working with the whole class of functions. For instance, we found that RAB is a linear space. Now, this was a additional structure on the space. Okay. Now, one could define, so being a vector space, one could also think of defining what is called the length. I just found that is merely a length concept. I said it is nearly a length concept because one could not assert that. Even when f is not equal to 0, you had this norm equal to 0. But except for this, one could do we have then now the 0 function has this property. This is the 0 function. So norm f defined what you call a semi-norm. So norm f fine, a now with now defining a relation Ri by zero. Now this means that f is equal to g everywhere except on see, now this is an equivalence. Now we define as the class of consisting of every gene is related F. Then being an equivalence relation, and the and is the space of all equivalence class. Functions on. Now that's the beauty. On this class, addition and scalar multiplication are well defined. It means defined without any ambiguity. To look for the meaning of this summons. And a linear space. Further, whereas it was a pseudonorm on RA. Okay. So we shall write So proper understanding of function. Oh, now this is an object. No. That is something. Having got a normed linear space, now you can talk about what are called distance. Now define that is equal to space. Here we are actually writing this one. So what you have, that's enough. This is exactly what it's a metric space. So we shall ask one of the primary questions that in an analysis. Now an analyst is natural. Whether space is complete. This is analysis concern. That is, thus a Cauchy sequence converge. Now this is the natural concern. What is the outcome? See, I'm not going to do it. I have done it earlier. You can look into it. Sorry, Riemann integration. It's possible. Now the answer is there exists Cauchy sequences which or converse. That means at times to chase a Cauchy sequence, just get out of the space. This is the point. Okay. Hence, the safe space is as bad as a unbarricaded, unbarricaded deck of a ship. May chase a sequence or chase a ball on the deck, a football game, we may end up landing in the sea. It's exactly that. You may get out certain sequences, you just chase, you just get outside the space. Therefore, it's not a safe place where one can do analysis. Okay. So we have done something magnificent so far. Started with a classical notion of antiderivative, introduced Riemann integral quite independently using geometry, and then connected them up using what is called the fundamental theorem of calculus. So it is the fundamental theorem of calculus which connected the two ideas. Okay. Then we found that the classical notion of a function, the antiderivative of a function with the function through the differential is not valid universally on this space, although for a very huge class of functions it is true. Okay. So the fundamental theorem of calculus was proved on this space, which is an attempt to connect the ideas. After that, we investigated the class of our Riemann integral functions, and we introduced a meaningful norm. I mean, meanwhile, the concept of norm, distance, metric, all these ideas had been in the air, and naturally people were investigating whether RAB with integral mod f is a normally linear space. It was found that it is not a normally linear space. In fact, it is an engineering feat made it into a normally linear space R tilde AB. Then the next step was to ask the question, is it complete or not? And it was found that it is not. I mean, that is a big disappointment at that stage. Okay. So RAB is not, in fact, you have this nice relationship. See? Take all continuous functions on the interval AB. Okay. This is contained, properly contained. This is a larger class of functions, but not large enough for completeness. Okay. So you ask, is there any completion? Any space? Now, this question essentially led to the construction of what is called integration. Now, this question led to the construction of a reconstruction of Riemann integral by introducing concept of measure for subsets of fine. Here one should realize that but what we have then is that it's available for all this, certainly for intervals. Effect measure coincides with its conventional okay, that's the story about the Riemann integral. Now let me just make some remark. One of the questions that you investigate is this, but this is not a part of this. Question is this: suppose f1 x converges to x as, or in other words, f1 converges pointwise f pointwise. There is a question: is f or we will assume assume f1 belongs to Ra. Is f This is one. The second question is, suppose and f is or in short what you are asking is, does the limiting process and the integral commute. Now these are some of the things that we see this. I mean, these are some of the standard things that we distribute. Okay, so there are very nice results regarding this. Under what conditions you can say that the integration, the limiting process can jump inside the integration and operate with this result. These are the questions that we have. I think that's a very nice place to stop and explore how we try to take up this completeness problem. This is our next lecture in the second part of this series, or the second lecture of this series. We explore how Lebesgue theory came about. In fact, I have done 80 sections of the whole thing, going through every detail of the construction, the consequences, and all these things. But we will just recall this so that before we go further to generalize this idea of measure and integration, it is better to be recalling all these aspects. So I think it's a nice place to stop, and we'll take it up in our next lecture. Thank you very much.